Hey everyone, welcome back to our next lesson. Today we're going to be talking about, finally, how to solve any equation using what we call the basic moves. Okay, so our lesson is titled The Basic Moves for Solving Equations. Before we get into any of this, let's shift our focus over here. Our mindset message today is that mistakes are really important. That's how you learn things, by making mistakes, right? So we should view those as an opportunity rather than a problem, right? And our learning goals for today, basically just one goal. Use the basic moves to solve equations. And we want to be able to tackle pretty much any equation that comes at us. Now, our prior knowledge would be remembering how to use backtracking, because remember, once we get an equation down to a certain point, often from that point on, we can backtrack. So that's a really important thing to remember. And then also what we studied recently, using models to solve equations. I think a lot of students sometimes can think like, well, if I already know how to use the basic moves, I don't even need to think about using models. But actually, we laid the foundation for why the basic moves work the way they do by learning how to use those models. And so I want you to always kind of keep in the back of your head, of course we know that drawing a model out for every equation is not necessary, or it takes a lot of time, right? But I do want you to remember that knowing how that worked is a very important foundation for you to actually understand in depth equations as we move forward with solving them. So to start things off today, here's the most important thing we need to remember for this whole entire lesson. So it's really, really, really important you have this written and that you carefully use this rule. Any quantity, okay, so that could be a single number, it could even be a variable, can be added, subtracted, multiplied, or divided to both sides of an equation to keep it balanced. Remember those models, they helped us show the idea of balance. Creating an equivalent equation. So this is a vocabulary word you need to know now. Equivalent equations are what result when we apply a basic move to both sides of an equation. So here's an equation. Here's a new equation that we got from adding or subtracting or multiplying or dividing by something. But those two equations actually are equivalent, okay, because it's been kept in balance. The only thing that doesn't work here is multiplying or dividing by 0. And that's really important to remember too. We talked about how doing that is not a reversible operation. So we can only do things that are reversible when we're applying the basic moves. So let's jump in right in and actually apply that to an idea. One idea here that's really important is understanding what equivalent equations are. So this equation given to you in number 1 here is equivalent to all the other 3 equations here. That means they have the exact same solutions. They are essentially identical. It's just there is a basic move you can do to move from one of these to the other, or maybe more than one move sometimes. So we want to describe a basic move that will transform this equation into each of the given ones. What I would ask you to do right now is at least just pause and take a moment to think for yourself what we might get. And remember, what you're saying is, oh, we would want to add this to both sides, or subtract, or whatever, okay? So, now that you've paused and you've answered this for yourself, let's just check real quick. Let's look here really carefully. What's the only difference I see in the left side and then the right side? It seems like this number is now this, right? And sometimes there's many different ways you could get from one number to the next, but in this case it looks like we're adding 2 to the left side. And let's check here. -1 plus 2 is +1. So this one we added 2. And remember, that means to both sides of the equation, right? So we did this, +2 and +2. We kept it in balance. Okay, part B. Wait a minute, this doesn't have any more p's over there. There was 2 p's, now there's none. But also these p's dropped by 2. Oh, I see. So here we subtracted 2 p's away from both sides of the equation. And again, we remember both sides, right? Because we had to keep it in balance. Now this one, a little trickier maybe. So the 2p plus 8 became 6p plus 24. Both of those numbers changed. And in fact, so did both of these numbers here. And if you look carefully, you'll see that we multiplied by 3. So here, we multiplied both sides by 3 to get this equivalent equation to the original one. Okay? So being able to actually look at two equations and see if they're equivalent or not and try to figure out a basic move or maybe more than one basic move that got from one equation to the next is really important to actually know. Now we'll apply these ideas to actually fully solving out some equations. So next, before we actually fully dive into solving equations, I really want us to remember and think about what it actually means to solve an equation. What we're trying to do is figure out a value for the variable that makes both sides of the equation true. But when we're actually going through and solving an equation, we usually want to get it all the way down to something that looks like this, that we can confidently say x equals some specific number, right? So this is a question that's actually asking us to work backwards, which sounds weird, but it will actually help us remember what our goal in the end is going to be. Essentially, we usually say isolate the variable, meaning we want x, or whatever the variable is, on one side of the equation and then a number on the other, because then we've stated, oh, x must be this number, right? I'm going to introduce you guys to something that I want you to maybe get in the habit of or in the practice of doing when you're solving equations. And I like to put a line through that equal sign. Now that's not the same as putting a little slash through it that says not equals to. This helps us remember the idea of balance, because a lot of times students forget and accidentally add or subtract when there is no equal sign. So always look for an equal sign, and if you see an equal sign with an equation you're solving, you can put a line through it to help you remember that's the balance. If there's no equal sign, you're not solving an equation. You're not adding or subtracting or applying the basic moves. So we're going to do this one together. You could think in your head there's different steps, but this is literally so open that we can choose whatever we want to do. Okay, so I'm just going to pull some things out of my head that we'll use here. So let's say first I decide to add 2 to both sides. And again, this line will help us remember what the two sides are. Well, what does that end up with? X plus 2 obviously is just x plus 2, right? And 3 plus 2, that can be combined into 5. And now I have an equivalent equation. If x equals 3, then it also must be true that x plus 2 equals 5. Let's do something else to both sides. Why don't we multiply both sides by 4? I'll multiply that by 4, and I'll multiply that by 4. And that's going to end up with, technically we could just leave this. You could distribute it if you want, but let's say we just leave it. 4 times parentheses x plus 2 equals 4 times 5 is 20. And maybe we'll just do one more thing, but again, don't forget where the equal sign is. Sometimes I think we visually think it's in the middle, but not necessarily, right? Just always think about the equal sign. Oh, what if I subtracted 3 from both sides? So what this whole thing ended up with here is 4 times parentheses x plus 2 minus 3. Notice none of that could be combined into one thing at this point. Equals 20 minus 3 equals 17. So what I've done is I've built an equation here. In fact, actually, I might do something even more interesting. Let's just use another x on here. And instead of 17, this will be 20 minus 3x. And I want you to be very careful. Those are not like terms, so they just have to stay like this. And then that would be minus 3x. So what I have here is an equation that I've started with a solution that I want, and I've built an equation using the basic moves that has that solution. So it's just like a working backwards practice, but it is helpful to help us realize that each green equation going on here has x equals 3 as a solution. We are going to be starting with equations like this and then applying basic moves. So if we actually started with this, we would be applying the exact opposite moves going backwards here, and we'd want to get to something that looks like x equals 3. Why don't you just take a stab at it yourself for this solution, x equals -2, and just build your own equation. in the same way that we did this. We're not going to come back and do it together because this is entirely yours to build, but I will look for it in your notes, okay? So why don't we actually move on to solving equations, and again, like I said, we're going to have some equations that are starting looking like something like this, and then we're going to work them down to being able to confidently say, oh, x equals some specific number. Now we should be fully ready to use the basic moves to solve equations by isolating the variable, okay? Now remember, to isolate means to get the variable all alone on one side. And if you want something that says x equals 5 or p equals 2 or whatever, right? An important rule to apply here is to always simplify first if possible, okay? And I'm going to still employ that rule that I shared with you here and ask you to remember where the equal sign is. If you draw a line through there, it'll help you remember where the balance is, okay? That's the balance point here. So let's go ahead and dive right in. If I want to isolate the variable, you'll notice here, all these equations, each of them has the variable on both sides. So none of these are backtrackable right now yet. We may get to a point where you have an equivalent equation as you're doing your steps, and it becomes backtrackable, but none of them are right now. So let's go ahead and start with this guy right here. If you notice that I've got some x's over here and some x's over there, it would be nice to have all the like terms together, right? And in fact, actually, that's something I probably should have put in our prior knowledge, and you can add that into the top of your notes right now, is that the idea of like terms is actually a very important idea we've learned in the past for this. So we know that 2x and 7x are like terms. So here's the thing, I would like all my like terms together, but you have these on this side and these on this side. What's going to make it so we have it only on one side? I guess it means we need to get rid of it on one of the sides, if that makes sense. So if there's two x's here, I like that there's fewer here than there. So I'm going to subtract 2x here, and if I subtract 2x over here, what's remaining is 5x minus 3 equals, that's gone, equals 7. And now what I can do is, I can backtrack it now, actually. So you could certainly keep going through and using the basic moves, but if you're comfortable enough, you can undo by backtracking in your head right now. I'm going to finish it out with the basic moves, but you are totally okay to look at this and say, oh, I know how to backtrack that in my head, and then just write the answer down. That's fine with me if you do that, okay? But if I was completely using the basic moves, I would add 3 here. And again, I am backtracking at this point, but I'm just writing it all out. And what it leaves me with is 5x equals 10. And this is, x is not isolated yet. Right now he's been multiplied by 5. How do I undo multiplying? Oh, I divide. I'm going to use the fraction bar for division here. And then what I get in the very end here is 10 divided by 5, right? So this becomes 1x, and 10 divided by 5 is 2. So my solution for that right there is x equals 2. Why don't you go ahead and pause and try to work the rest of these out on your own right now. Okay, let's take a look at our steps together. Remember how I said simplify first if possible? That's always a good thing to keep in mind. I will draw the line here, and we could certainly put some like terms together. However, you'll notice that we have some like terms here already on one side. So it's always a good rule of thumb to simplify first. So what we're going to do is, we're not going to do anything, we're not going to do any balancing right now. We're just going to put these things together. 2m minus 6m is negative 4m plus 9 equals 3m minus 5. Now I can treat it like I did that one from the beginning. This is totally up to you what you want to do. The fact that I see negatives here, I kind of like to not have negatives if possible, not have to deal with them. So if that's a negative 4m, I'm actually going to add 4m's here, but if I do that, I must add 4m's there. Don't forget that idea of balance. And what that's going to leave me on the left side is these cancel out, right? That just leaves 0. So I have 9 equals 3m's plus 4 more m's gives me 7m's. And then I have not done anything with that minus 5. And yet again, we can now backtrack, right? So I'll add 5 here and add 5 there. And I get 14 equals 7m. And then again, I get to something that's being multiplied, so I'm going to divide it. I forgot to draw my line there. And in the end here, I get m equals 14 divided by 7 is 2. So m equals 2. Coincidence that they're both 2. This one, we've talked about how even if you distribute, it's not necessarily more simple one way than the other, but it is helpful with the basic moves if we distribute. So most of the time I would say distributing is something you want to do as soon as you see that you can do it. And you probably already noticed that. So again, this is one where I don't need to do any balancing yet. I can still draw that line to keep in mind the equation. But first, before I do any balancing or apply the basic moves, let's do this idea of distributing and just rewriting it. So if I distribute this 3 across p plus 4, I get 3p plus 12. And if I distribute this 12 across p minus 2, I get 12p minus 24. And those are equal. Now yet again, we've run it into something that looks similar to what we started with in part A, right? And we can combine like terms on one side of the equation and then the numbers on the other side of the equation. So let me just run through this. Minus 3p, that's what I'm going to do here, and that leaves that. So I have 12 equals 9p minus 24. Now I can backtrack. So plus 24 plus 24, and that gives me 36. Oops, I'll keep that there. Equals 9p, and yet again, I will divide by whatever's multiplied into p, divide by 9, and in this case we get p equals 4. So there's our solution for that. And last but not least, you may have come into some trouble with part D. I snuck that in there on purpose, because watch what happens if we try to combine like terms. Here's 2y's and 2y's. Now you may think about something we've already talked about. You probably can look at this and see there's something wrong with it, actually. Because watch, if we try to apply the basic move by combining like terms there, if 2y is taken away from both sides, there's nothing left, but there's also nothing left. Here what I'm left with is 3 on this side and 8 on that side. And when I've taken 2y's away both places here, there's nothing left from that. So there's no variable remaining, and all that's left is something that says 3 equals 8, which you and I both know that can't be true. And of course, if you look back at the beginning here, we can see that 2y is the same thing on both sides. And there's no way that adding 3 to that could be the same as adding 8 to himself. That just can't be true. So this is one of those equations that actually has no solution. But now that we've learned about the basic moves help us confirm by seeing, oh, that can't be true, that there just is no such thing. There's no number for y that could ever make that be true. Let's jump into a couple more, maybe more tricky equations before we finish off.